Hi viewers, welcome to all. Here we are discussing about the project low cost online convolutions checksum checker. In this method, a random hardware defects the fault need to be recognized on online in order to more accurately manage random hardware issues. This makes recovery much easier. It has been suggested the algorithm based fault tolerance might be used as a low cost technique to validate these results for computations online against the possibilities of random hardware failures. In this instant, a hardware checker compares the checksums of the actual results to protected checksums that was calculated in parallel by the checker. Okay, so in this proposed work, our primary focus is on the creations of checkers for convolution engines, which were the fundamental component of the image processing and digital applications at the present time. Okay, so ConvGuard is a name will be created on this project. It's given the proposed convolution checksum checker that makes use of the recently developed invariance conditions of convolutions. Okay, so the ConvGuard taken the amount of power that is for the accumulations of the input pixels without the need for huge buffer to store the intermediate checksum finding. Thus, the proposed work developed with the ConvGuard method using reversible logic gate to reduce the amount of power and logic sizes and the accumulations of the input pixels without the need of huge garbage signals. Okay, the result of this experiment reveals that the ConvGuard uses just a tiny protections of the space and power of an effective convolution engine. Finally, this work was built in Verilog HDL and synthesized on Xilinx Vertex 5 FPGA and compared all the parameters in terms of area. Now we can verify the base paper. This is a base paper title and base paper abstract. Here base paper title low cost online convolution checksum checker. Okay, so here checksum is a most priority one for security purpose of data transmissions and reception from one end to another end. It will be used for image processing, signal processing. Okay, whatever packet of data you need to transfer from one place, we can use a checksum. Okay, and CRC based security method. Okay, so here they are used this convolution checksum checker. It's mainly focused for the CNN method. Okay, CNN means it's a convolution neural network method. They are used this convolution checksum checker. Okay, and this proposed work of this paper they are used for strided convolution checksum checker. Okay, so this strided convolutions means you can check with this link. It's having a different types of convolutions in deep learning method. Okay, so this is one of the convolutions method. Okay, and 2D convolution using kernel size of 3 stride and 1 and padding. Okay, and this is another one. Okay, dilated convolution. Okay, and this is a transpose convolution. Okay, separatable convolution x and y filters. Okay, so we are use this filter coefficients for our purpose also. Okay, here we are developed with the strided convolution. Okay, here this is a basic architecture of the checksum method, online checksum checker. Okay, so once the input came, it will given into the convolution engine. That means you are having any encoder or you are having any decoder, so that architectures will be developed in this area. It's a convolution engine. So the input data parallelly given into the protected checksum and calculated it. Okay, and that protected checksum and the output of the checksum. Okay, it will be calculated and both will be compared. Okay, if it will be equal means it's error equal to 0, if not equal means error equal to 1. Okay, so this is a part for online checker. Okay, here in the paper they are focused with CNN network means it's related with image processing. Okay, so based upon that they are handled with number of matrix based method in here. Okay, so here this is a one of the example. The figure 3 shows the existing method of the ConvGuard convolutional engine. Okay, so here they are given again the x of n equal to input. Okay, so x of n they are given, and it will be parallelly, it will be given to the number of accumulators. Okay, so this is the accumulators. It's same like as a filter. Okay, filter means FR filter, it's having a adder, delay and a multiplication part. The both three it will be given on here, that is called a accumulator part on here. Okay, so based upon this accumulators they are used number of additions, and finally they are taken the predicted output checksums and output checksums and calculated the error value. Okay, and this is a convolution part. This is a existing method of this paper. Okay, so it's having the code in Verilog HTL. Okay, we have developed the code for this part also. So this is a convolution engine for ConvGuard, and this is a test bench of the code, and this is a top model. And this simulation coding we are having here, it's random modelism. Okay, so you can check the input value and output value. Here this is a xn input and this is output pixel. Okay, and this is a common addition, one sum addition, sum value, subtractions, multiplications, okay, additions and comparing value, and convolution engine part. Okay, and this synthesized report, we are synthesized this in vertex 5 FPGA. Okay, and it's having a number of slice registers, LUTs and occupied slices. Okay, and IO bus. Okay, and delay you can check down here, delay equal to 1.828. so it will design in reversible logic gate. Okay, we have developed this existing part and proposed part, both we are developed in convention method and reversible logic method. Here also it will develop in reversible logic gate. Okay, full adder part in Fredkin and Feynman gate, and half adder part also Fredkin and Feynman gate. Okay, and subtraction part also developed in reversible logic gate. Okay, so here the full subtractor, here we are using the Fredkin and Feynman gate. Okay, okay, and the next part of this paper is a strided convolution method. Okay, so this is a strided convolutions method. Here they are given one transformations of the strided convolution with s equal to 2 to a 4 channel unity stride convolution. Here based upon the s equal to 2, we can give s equal to 1, s equal to 3. Okay, so that is another part, but in this paper they have developed only the s equal to 2. It's having lots of proposed. Okay, if required we can develop it. Here this paper, the s equal to 2 method means they are used the 2:1 method. Okay, here that means x00, here we are taken means the next pixel they are omitted, and after that they are taken as a x02. Okay, that means 2 pixels once they are taken the value. Okay, so based upon that they are plotted this blue pixels, yellow pixels and orange and green pixels. Okay, and it will be multiplied into the kernel method. Okay, so kernel means it's a coefficient. Okay, the coefficient method, it's also the same as a filter coefficient method. Okay, and after that they are taken as a output, the blue, yellow, orange and green. Okay, and it will be added the final addition. Okay, this is a predicted output checksum method, right? Okay, so this is a final addition, and it will be given into the output. Okay, so this functionality of the blue, yellow, it will be given in blank. Okay, but we are described this in Excel. Okay, so how it will be predicted. Okay, based upon that we are written a code for this project, and this is a figure 7 generalized ConvGuard architecture for strided convolution. Okay, so using decoder we need to mask which bit you are needed and which bit means which accumulator you are needed and which accumulator is not needed. Okay, based upon that it will calculate the predicted output checksum. Okay, and this coding part we are developed in Verilog HTL. So this is a test bench of the code, and this is a top model of the code, and this simulation we are running model sum. Okay, so here you can check the model sum output. Okay, so this is output for you can show it parallelly. So this is a output for started method, and in the top it will be showing right hexen and output pixel. It's the convolution part. Okay, you can check both outputs. Okay, and here also we can show the common addition, one sum addition and sum value, and subtractions, multiplications, additions. Okay, comparing the value. Okay, and decoder part. Okay, so here decoder is the main priority one. So based upon the decoder we can choose the standard method, which pixel we need to add and which pixel we not need to add. Okay, so based upon that we have created the code, and this is a synthesis report for standard convolution engine. So number of slice registers, number of LUTs and occupied slices, IO base. Okay, and here the synthesis report you can check it. Okay, here delay will take 1.883. so this comparisons we are updated in the comparison table. So this is a comparison table. Okay, so here you can check the convolution checksum checker, conventional logic gate and reversible logic gate method, and standard convolution checksum also designed in conventional logic gate and reversible logic gate method. And this is a comparisons analysis chart. Okay, and this is a document and report. Okay, so here you can check the title, base paper abstract, announcement of this project, proposed title, proposed abstract, existing system, desired teachers and proposed systems. Okay, advantages and related notes. Okay, finally literature survey and references. Okay, thank you.
If you need more video related with VLSI projects implementation, please like and subscribe this channel.